And as the drugs have gotten more complex, I mean, they used to be small molecules. Then they became biologics, proteins. We heard about CRISPR. Drugs become more and more complex. The delivery systems must become equally complex. And that's really a key part of our research. How do we develop these technologies which will bring out the best therapeutic value from these drugs?
I mean, as a physician, I think about the importance of a patient actually adhering to the regimen you prescribe. And if you're prescribing an injection, you have to imagine a great motivation for the patient to keep up with that. But even if it's, you know, if you can change a formulation so that you only have to deliver it once a week rather than daily, or once a month, or even once a year, that makes a huge difference in the ability to actually treat your patient.
Absolutely. The non-compliance with diabetes medication is huge. So data show that nearly half the patients do not take their insulin as prescribed because people don't like injections. There is pain, there is needle phobia. The sight of needle piercing the skin is not very pleasant to watch.
I noticed a number of people fainting once we saw that.
I'll be one of those. And I think if there is no immediate consequence, patients tend to just delay the medication.
Right.
But these delays eventually catch up. There are long-term complications of non-compliance. So it must be, a method for delivering drug must take that into account, something that makes it easy for the patient to take the medication. And that's where oral delivery, I think, really shines. We are all used to taking pills. It is part of our routine for many situations. But that route is not open to proteins, and that's what really motivated us to figure out a way to deliver proteins orally.
You've been an innovator in lots of different vehicles of altered drug delivery. I mean, what are the strategies for being able to, put drugs on a particular schedule, that maybe is run out of your iPhone, or, the kinds of modular strategies that allow us to deliver medications?
I think there are lots of opportunities and lots of innovations in this field. I guess, different drugs require different strategies. For some drugs, you just need to deliver a predefined dose at different times. For certain drugs, you had to really get some feedback from the body to figure out what dose to deliver. And that really results into two challenges. One is to how do you actually control the schedule? And once you know the schedule, how do you actually release that particular amount of drug from the vehicle that you're administering? And that's where our research and others as well is largely focused on, is encapsulating drugs in formulations, in nanoparticles, in depots.
Chips even, yeah.
Absolutely, and making sure that the carrier stores enough drug and then releases it in response to a trigger. Whether the trigger comes from the patient, from a measurement, or it comes from a biological measurement, but the goal is to deliver drug in a way that makes the most effective use of the drug at that particular time.
Now, I know that you're an engineer. What does engineering bring to medicine? What attracted you from this other field to move into the life sciences?
And to me, engineering has three key steps. The first step is to understand. The second is to reduce the understanding into laws that can predict the behavior, especially of the complex systems. And the third is to take this understanding and these laws to develop useful treatments, modalities. And what better playground than the human body to implement these? Human body poses tremendous challenges. There is a lot to understand. There is a lot to model and lots of things to fix. So as an engineer, I was always fascinated by these medical problems. So I did not take any biology classes until I actually came to my grad school. But when I became aware of this challenge, I was just fascinated by how effectively we can use this engineering principle to solve unmet needs in medicine.
Wonderful. I'm so glad that we've invited our engineering colleagues into our playground for the life sciences. So, thank you. Thank you so much. Great. We'll turn to the next video.
If this were easy to solve, someone would have already solved it. About a third of the world's population is at risk of malaria. There are over 200 million new cases each year and over 500,000 deaths, primarily in children in Africa each year. Malaria is an infection caused by a protozoan parasite. It invades the human first by the bite of a mosquito and then goes to the liver and then goes to the red cell. My lab focuses really on understanding the parasite and the parasite's biology through the lens of genomics. It's really using genomics to understand how the parasite overcomes drugs, develops resistance or tolerance to drugs, and how the parasite is able to evade the human immune system. We have collaborations in countries all over the world. Our students have the opportunity to participate in work in natural settings and then come back to the lab and apply cutting-edge genomic, cell biological, molecular biological techniques to really eradicate the disease in the areas that are most affected. One is going to need something that's long-acting, and there I think the opportunity for discovery and development of an effective vaccine is the most important innovation. You know, it's a challenge. There's no question that it's a challenge, but malaria is not a disease that afflicts people with great wealth. It is a disease of poverty, and thus progress in malaria is going to depend on universities and governmental funding because it doesn't have a private sector profit that could be used to develop innovation. So I think Harvard has both a responsibility and an opportunity to make great advances in this field.
Good to see you. Genomics. I understand your laboratory looks at this problem in part through the lens of genomics, and genomics has revolutionized our understanding of human genetic disease, a variety of other areas. What is there a malaria genome project? Where are we? And how do we learn about malaria through the lens of genomics?
Well, you know, genomics, as you say, has revolutionized lots of science, but for infectious diseases, it's really completely changed the game. We now understand every gene of the organism, and we can look as the organism becomes, say, resistant to drug. We can simply look at the genome and identify the single mutation that leads to that resistance. And so this allows us both to understand, it also allows us to think about new ways to develop drugs, and it allows us to look at the impact of drug resistance in the population.
Mm-hmm. So most often, if a case comes forward with malaria, we react to it with a drug, trying to eradicate it. But as with so many diseases, vaccines are really the strategy. Why don't we have a vaccine for malaria?
It's a great question. I mean, one of the challenges with malaria, unlike, say, measles, where we do have an effective vaccine, is that each time you get infected with the malaria parasite, the parasite is able to express a different set of proteins on the surface. So it has this vast ability for antigenic variation. Sort of flu is in some ways a simpler version of that antigenic variation. The reason we need a flu shot every year is because the flu virus has changed from one year to the next. And in malaria, that happens each time a person is infected. And so I think the challenge is, how do you design a vaccine for a disease where infection with the disease doesn't lead to long-lasting immunity? It's a challenge, but I think it's one that we're ready to undertake.
Mm-hmm. Well, it's obviously a big challenge, because you said if it were easy, it would have already been done. Right. But what are the other barriers? I mean, this is a disease that's not widespread and endemic in the United States. Mm-hmm. The question is, where do you get your funding, or is funding one of those barriers? And how do we approach this from a public health point of view?
Right, exactly. One of the challenges is it is not a disease of the developed world, so one's really dependent on government, on philanthropic organizations. The Gates Foundation, for example, has made this a very important part of their portfolio. The Global Fund pays for introducing treatment. So, I mean, the challenges are many. This is a disease of poverty, but it's also a vector-borne disease. So the mosquito, which carries the disease, is able to sort of amplify. So a single person can lead to 100 new cases because a mosquito bites that person, or many mosquitoes bite that person, and then can transmit to additional people. So the disease is a challenge both in terms of its immunology, the human immune response, it's becoming resistant to drug, and it's a vector-borne disease, so that allows this major expansion.
I want to just change gears for a moment because you have been a leader in education, and I want to talk because you've been a major force in the Harvard Integrated Life Sciences community, and the young people in our community play such an important role in our own science.
Right.
What advice do you give to young people in thinking about their future as biomedical scientists?
Right. I mean, this is such an exciting time in biomedical science. The tools that we're hearing about today are making things possible that weren't even a dream a few years ago. So this is a great time to enter the field, and it's a great time to make a difference in important diseases like malaria. I also spend a fair amount of my time, as we do in general at the School of Public Health, also training scholars from around the world, because I do believe that creating the intellectual infrastructure in Africa, in Asia, to be able to directly solve these problems in country on their own with collaborations is in fact the future, and I think it's really a very bright future.
Wonderful. We have the privilege of being a magnet for not only the best and brightest students from here locally and in our own country, but we're increasingly drawing individuals from around the world, and then it's wonderful to train them, enable them, and send them back in a way that Harvard is having an impact really globally. Wonderful. Thank you very, very much.
Thank you.
Okay. And on to our next video.
We saw a patient with a disease that nobody had ever seen before. The patient rapidly died, and then we saw another. And then we saw another, and that was really the beginning of the HIV epidemic. I realized then that we as physicians on the front lines were going to be the people to see new diseases, and if we didn't do research, we were going to watch a lot of people die. And that, to me, is really what research is about, and that's why it's so critical. There are 36 million people that are already infected. Only half of those have access to therapy. Without lifelong therapy, the virus will win the battle. My research in HIV/AIDS is trying to solve two problems. One is trying to prevent people from becoming infected, and the other is trying to do something for the people that are already infected by developing a vaccine that could teach their immune systems to do a better job of fighting HIV infection. And the way that we're approaching that is to try and learn from people that spontaneously control without medication, learn what it is that they're doing so that we can try and replicate that in other people. We were able to bring resources that were available to us here to South Africa, to the heart of the epidemic, create 2 institutes there to tackle the biggest health problems they've got, to bring multiple other Harvard scientists into the mission, and to work with our collaborators to train a next generation of African scientists. And I feel really proud of that. What has become extremely clear to me from our work in Africa and also from our work in Boston is that none of these diseases is just a scientific problem. None of them is just a social problem. None of them is just an economic problem. It's all of these things wrapped together, and I think that's where an institution like Harvard has the ability to make a tremendous impact. There is so much talent in this couple-mile radius of hospitals and research institutions and universities. It's really unparalleled. There is no better place to create knowledge than here, and I have to say, I love being here.
Great. How long have you been here?
I've been here for a long time. I came in 1980, right at the beginning of the HIV epidemic.
Wonderful. Well, so you learned about HIV really through your clinical practice here in our hospitals, and yet you've now extended this clinical practice globally. Mm-hmm. Where are you working, and what is it that this international sort of global presence brings to your own work?
Yeah, I think in order to understand and solve global health problems, we have to understand them in their global context. And HIV infection is a great example of a global disease. If you consider the epidemic in the US right now, it's a treatable disease. Children miraculously are no longer being born with HIV infection because mothers are getting diagnosed